Can you guys hear me? Can you guys hear me? Hello, can you hear me? Christopher, can you hear me and see the screen? Hello, can you hear me and see the screen?
Yes.
Okay, I'm going to mute you then. I'm going to mute all, and then Christopher, can you hear me now?
Yes, I can still hear you.
Okay, all right. I think we're ready to go. Okay, good morning. I hope you guys can all hear me well and see the screen. I'm trying something different today. I'm actually teaching from home, so hopefully there won't be any snafus. Can one of you unmute yourself and confirm that she or he can hear me and see me? Did they see the screen?
Everything is good.
Okay, good. Thanks, Frank. All right. So last time we were talking about heterostructures, hetero meaning two different materials that are joined together, and we wanted to find out how to draw the band diagrams. Now, in the context of heterostructures, differences of doping don't count. So the p-n junctions in silicon that we've been talking about so far would be homostructures, not heterostructures, because there the band gap throughout the system is uniform. Okay. Now, if you have two dissimilar materials with different band gaps, or maybe one of them is a metal without a band gap stuck on top of a semiconductor with a band gap, then something funny with Zoom, the default is everybody is admitted, but then for some reason, some people have problems. So I have to let them in individually. Sorry about the pause. Anyway, so heterostructures refer to two dissimilar materials stuck together. And the question is, how do you draw the band diagrams? What would be the IV and CV characteristics? We started discussing that last class. And just to refresh your memory, we said that you always draw the band diagrams, which are these plots of electron energy going up on the vertical scale as a function of position x, where we know, of course, that the band edges are only electron potential energy at the conduction band edge. And as you go up, you add kinetic energy to the system. Similarly, over here, it's only hole potential energy, and hole kinetic energies go downward, increase downward. Potential energies, of course, are relative quantities. So you discuss potential energy in this context with respect to what's called the vacuum level, which is shown at the top, which is this common reference potential energy that electron would have if you pulled the electron out of the material out into space where it's not seeing any electric fields or whatsoever. Okay. Now, with respect to that vacuum level, which I'm calling EVAP, there are two quantities that one defines to characterize the material. One of them is the so-called electron affinity, chi. In energy units, that would be Q times chi. And once you know that, you can immediately, of course, pinpoint the location of the conduction band. And then, of course, if you know the band gap, you can also pinpoint the location of the valence band. The other parameter that you need to know is the so-called electron, the work function of the material, phi, either in the semiconductor phi s or in the metal phi m. And what that is the difference between the vacuum level and the Fermi level. Okay. So knowing the work function, the electron affinity, and the band gap, you can pinpoint the three key points: conduction band edge, valence band edge, and the Fermi level. Okay. Now it's important to know where the Fermi level is, because when you stick two materials together, we know that in equilibrium, Fermi level has to be constant everywhere. The Fermi level is also known as the electrochemical potential of the system, because part of the driving force of the carriers is electrical in nature. That's a drift current that's given by gradients of the electrostatic potential. But part of the driving force in a material we've seen is diffusion, which is governed by concentration gradients. Now, concentrations are characterized in thermodynamics by a quantity called the chemical potential. Therefore, driving forces due to diffusion are considered to be driven by differences of the chemical potential. And since in general you can have both drift and diffusion, the overall driving force is called the electrochemical potential, and that is also known as the Fermi level. And the analog that we used was its analog of water pressure or hydrostatic pressure. And just as water flows from a high pressure region to low pressure region until in equilibrium, the water pressure is the same everywhere in a set of interconnected cylinders. Similarly, in materials, when you join them together in equilibrium, when carriers spill over and everything settles down, the Fermi level has to be constant everywhere, okay? Now, mind you, of course, that these are dynamic equilibriums, meaning that it's not as if all the electrons and holes are totally static at that point. They still flow backwards and forwards, but there's no net flow of electrons or holes either way, okay? The question, of course, is how do you draw the band diagram of such a heterostructure? And you should be prepared to do that in the final exam. So the first thing, as I said, is you draw a horizontal line and you call that the Fermi level, because you know that it's going to be constant throughout, okay? And you draw the rest of the band edges with respect to that constant Fermi level. And you start first far away from the junction, because at the junction, that's the most tricky part. You don't know how things are aligning and bending and all that, okay? So very far away, we know that the conduction band edge will be that far above the Fermi level as it was before contact, right? Because that's a measure of how strongly N-type this semiconductor was, okay? And presumably very far away, the electron concentration won't change a whole lot. Therefore, you can draw the conduction band edge above the Fermi level, the same as it was before contact, okay? And once you know that, you can immediately write down, pinpoint the position of the valence band. And as the bands bend, of course, band gap can change. Therefore, the EC and EV must be parallel to each other all the time. So if you end up with a drawing where somehow EC and EV are not parallel, you've messed up somewhere, okay? So then the trickiest part is what happens right at the junction, right? Now to do that, the best way is you look at the diagram just before contact, as shown over here, and you simply extrapolate the lines, okay? So if you extrapolate this, you see that EC to EFM, the Fermi level in the metal, is obviously given by phi m minus chi, right? And therefore, that's the barrier height over here for electrons in the metal spilling over to the semiconductor. Now, metal, of course, doesn't have a band gap. Therefore, there's only the Fermi level that you need to worry about. In a second, we'll look at two different semiconductor heterostructures, in which case there'll be band gaps on both sides. So that's a more complicated scenario, okay? Now, in this particular case, we see that electrons are spilling over from the semiconductor, which is N-type, because the Fermi level was closer to the conduction band edge, this way, right? Because electrons always flow from high to low Fermi level region, and holes flow the other way around, okay? And mind you, it's doing that despite the fact that a metal typically will have a lot higher electron concentration than even a highly N-type doped semiconductor, okay? So you should always think in terms of the relative positions of the Fermi level. Now, if the electrons, which are the majority carriers, spill over this way, clearly I'll deplete the majority carrier concentration in the semiconductor. And in the process, I'll be exposing these positively charged immobile donor ions, okay? Kind of like in the depletion region of a PN junction. And because I have lower electron concentration over here, that's reflected by the conduction band moving away from the Fermi level, okay? And you create a barrier. The question is, what is the height of the barrier? That works out to phi m minus phi s. How do I know that? Well, I have to move this EFS down by phi m minus phi s to line up the Fermi levels, right? Therefore, that's how much the barrier is, phi m minus phi s, all right? At this point, as I said, it's not a static equilibrium. So now what will happen is I still have electrons, but of course you have fewer electrons higher up in energy, and you have more electrons as a function of energy down below. So it's only those electrons high up in energy which have enough energy to spill over this way, right? Diffuse this way. And that small trickle of electrons is going to be counterbalanced by the few electrons in the metal which diffuse this way. And there'll be an equal and opposite flow of electrons and no net current, okay? But then if I forward bias this is a so-called Schottky diode, okay? A metal semiconductor diode like this is like a Schottky diode. So now if I forward bias it by V, the barrier reduces from the starting value V0 to V0 minus V, just like it's in a PN junction in forward bias. So now you have more carriers at this lower energy, obviously, that can spill over. The opposing current doesn't change because this barrier isn't changing. And therefore, you end up getting this sort of an exponential dependence of current. Here I'm showing current density, amps per centimeter squared. To get the current, you have to multiply by the total cross-sectional area A of the device. Don't confuse that cross-sectional area A with this A star. A star is known as your modified Richardson constant. Richardson was a British physicist who analyzed this, and he won the Nobel Prize in Physics in the 1900s, okay? V thermal is your thermal voltage, KT over Q, and V applied, of course, is your applied voltage. It could be forward bias, in which case the barrier will go down, or reverse bias, in which case the barrier will go up. Obviously, if the barrier goes up, there's so few carriers over here that this flow basically is zero. The opposing current doesn't change, and therefore you'll have a reverse saturation current given by this, which is this value over here. Okay. You can analyze the electrostatics of the junction also by solving the Poisson equation. Exactly the same math as in the case of a p-n junction. And then you can relate the depletion charge QD to the applied voltage. You define capacitance not as C over V. So in the last class, we looked at capacitance. And we said that if you have area of the electrodes, epsilon, thickness of the dielectric W, and the dielectric constant, epsilon, then the capacitor is given by area of the capacitors times epsilon divided by the thickness of the dielectric. So if I now put a charge plus Q on one electrode and minus Q on the opposite electrode in a fixed parallel plate capacitor, Q over V will be a straight line, and the slope is what I call the capacitance, okay? But in a semiconductor device, you'll get some nonlinear dependency, and therefore you have to define capacitance not as Q over V, but dQ over dV, or in other words, a slope at different points. And the slope varies, and therefore you get a voltage-dependent capacitance. All right. Now that was a metal N-type semiconductor Schottky diode. This shows the same behavior for a P-type semiconductor. Now the Fermi level is closer to the valence band. Electrons are obviously going to spill over this way, meaning that holes spill over this way. And I'm forming a depletion region as shown over here. I expose negatively charged acceptor ions. It's the same story, okay? Now, one comment that I want to make in passing is what I've just told you is sort of the 0th order model, okay, the most simplistic model. If you take a graduate course, which I'm sure you will because you love the subject so much, you learn more complicated things like something called Fermi level pinning. Okay, what does that mean? Well, it turns out at this interface between the semiconductor and the metal, you're liable to have a lot of defects because, you know, after all, you're sticking on different material on top of the semiconductor. So you can get maybe a lot of defects in the middle of the band gap somewhere, okay? If you have that, then the Fermi level will be essentially fixed or pinned at that location, because small changes of the band bending at that point will cause huge changes of the charge occupancy at these defect sites. Because remember, any defects below the Fermi level would be occupied by electrons, while defects above the Fermi level will be empty, okay? So these will be occupied, these will be empty. And if I have a large defect concentration at some energy, small changes of the band bending are enough to take care of the charge changes that you need, okay? And therefore the Fermi level is actually pinned at that defect energy level, and it's not governed by the simple band alignments that I've been talking about. All right, so much for Schottky barriers or Schottky diodes, okay? Now when you stick on a metal on a semiconductor with a different set of parameters, you end up getting what are called ohmic contacts, okay? Ohm's law is V over I equals to resistance. So that's a straight line if I plotted V over I. So you get a similar V over I, which would be a resistor. The slope is a resistor. Or conversely, if you plot I over V, the slope is given by the conductance, right? Now, these are, of course, for fixed resistances or conductors. And a semiconductor, similarly, you get a nonlinear dependency. And then you have to define conductance, for example, not as I over V, but DI over DV, just like in the case of the capacitance, and that gives you a voltage-dependent conductance, as for example, that you'd have in the case of a p-n junction, right? A p-n junction has a nonlinear IV. All right, so what gives you an ohmic contact? Well, all that I have to do is change the system parameters, and in this particular case, I've chosen a value of the work function in the metal such that the Fermi level in the metal was higher than the Fermi level in the semiconductor, okay? I've kept the semiconductor parameters the same, say. But in this case, obviously, then the electrons would spill over this way. The N-type semiconductor already had majority carry electrons. If I spill over more electrons from the metal, I don't form a depletion region. The conduction band edge bends even closer to the Fermi level. and that is known as accumulation of carriers, okay? That's called accumulation of carriers, okay? There's no depletion region forming. Now, if that happens, clearly, for these majority carrier electrons, there's no potential energy barrier. They can flow very easily this way. And similarly, the electrons in the metal can flow back and forth very, very this way. And you end up getting an IV, which is not like a diode, but more like a, sorry, let's look at this one. So if I plot I as a function of V, you'll end up getting more or less something like this, okay, instead of a diode type behavior. And that's, of course, like a ohmic resistor. Now, it turns out, in this context, you really care about the slope of this IV. Okay, so if you had a choice between a curve like this, which has a perfect, it's supposed to be a straight line, like this, versus a wiggly curve like this, I call this case B, I call this case A. Although A is a linear IV, while B is nonlinear, from a practical point of view, which one do you think you'd prefer? Remember, I am sticking on a metal wire to my semiconductor device to get current in and out, okay? So although A is a true ohmic behavior, while B is non-ohmic, which one do you think is better from a practical point of view as an ohmic contact? Anybody?
B, because there's less resistance to current flow.
Exactly, very good. So B, because you don't want to waste any voltage across this metal semiconductor junction, right? The wire to the semiconductor. You want most of the applied battery voltage to be applied to the semiconductor device itself, be that a diode or a transistor or what have you, okay? And we'll see in a second how you can cheat and you can make functional ohmic contacts, okay? That's described down below. All right, so that's the true ohmic contact for an N-type semiconductor, and down below is a true ohmic contact for a P-type. So in this case, the electrons spill this way, or in other words, the holes spill this way. Now, holes are the majority carriers, therefore I form an accumulation layer of holes, which are mobile. Here I have an accumulation layer of electrons, okay? So going back to this cheating business, so sometimes you may not be able to get a true ohmic contact. In fact, if I work with one kind of metal wire, say aluminum, clearly you can see you cannot possibly have a true ohmic contact to both N and P-type semiconductors, right? And that's a problem because, you know, when I make an IC, we'll see that you'll have typically both N-type regions and P-type regions. You have NMOS and PMOS, and you're not going to change the metal wiring on the IC separately for the N and the PMOS. It's just impractical, you know, too complicated. So you'll be dealing with only one kind of metal wiring, which has a certain work function. Therefore, clearly, if it's a true ohmic contact on N-type, by definition, it has to be a Schottky on the other type, or vice versa, right? So how do you cheat for the other one, okay? So what you do is, on the one where you normally get a Schottky diode, you make the doping in the region of the semiconductor where the metal touches it very, very high, okay? How would that help? Well, go back a couple of slides. So if I made the doping in the semiconductor very, very high, what do you think will happen to this depletion region? It'd get narrower and narrower, right? And the band bending would be like this, right? If the band bending is like this, and this barrier becomes very, very thin, do you remember how carriers can flow across that? Do they have to always go over the barrier, or is there another option?
They can tunnel.
Tunneling. Yeah.
Very good. They can tunnel through, right? So you always, just to hedge your bets, whenever you put a metal contact to a semiconductor device, that region is generally going to be very, very heavily doped to kind of guarantee that you'll get an ohmic contact on both sides, okay? And under those conditions, a tunneling IV may not be perfectly linear, but you don't care. As long as I can get a lot of current flowing through for a small applied voltage, I don't waste a lot of voltage across the contact. That's what I mean by functional ohmic contact. Now, there are more drastic ways, which are not really practical on the front side of the device, are to purposely create defects in the device. And we have seen that in a PN junction, if you have a lot of defects, you get a lot of leakage current, you can play the same trick also. But that's not really a practical way on the front surface of the IC. People will sometimes do that on the back side of the wafer to make a contact to the back side. Okay. All right. So now to conclude our discussion about two-terminal devices, I want to walk you through drawing the band diagram of a heterojunction. Now I'm looking at two different semiconductors, a semiconductor 1 joined to semiconductor 2 instead of a metal joined to a semiconductor, okay? Now here, since both are semiconductors, obviously I'll have two sets of band gaps, EG1, EG2, two sets of electron affinities, chi1, chi2. So knowing those and knowing what the vacuum level is, I can pinpoint on both sides where the conduction bandage, valence bandage, and the Fermi levels are, right? So if I give you a problem like this in the finals, and there's a very good chance I will, because this will require to think of everything that I've been talking about for the last few weeks, the first thing that you should do is look at the problem statement and draw the band diagram before contact, as shown on the top figure, okay? And put down the numbers, okay? Then, to draw the band diagram after contact, you close your eyes and you draw a horizontal line and call it the Fermi level, okay? Very, very important that you close your eyes, otherwise the math doesn't work out, okay? So close your eyes, draw a horizontal line, call that the Fermi level, okay? And then you start drawing the band diagrams. Now you open your eyes. That was a joke, right? I mean, you can keep your eyes open, of course. I don't want, scrawly lines all over the exam paper. You first draw the band diagram far away from the junction, because you know that the carrier concentrations will not be perturbed very, very far away, right? So you draw EV and EC just as before contact on this side and same over here, okay? The hardest part, of course, is what happens right at the junction itself, all right? So first of all, you need to figure out, am I forming depletion regions or accumulation regions? And to figure that out, you have to see where the Fermi level is higher. So here, I see that the Fermi level is higher on the right-hand side. So electrons will spill over this way, holes will spill over this way. Okay, now in this case, I've chosen parameters where this side is N-type, this side is P-type, clearly. So I've chosen parameters where both the N side gets depleted as well as the P side gets depleted, right? So I have formed depletion regions on both sides. Now, I only could have changed one parameter and the whole thing would have changed, right? So for example, if I kept reducing chi1, right? What's going to happen? The left-hand side band will keep moving up, and at some point, EF1 would move higher than EF2, right? So what's going to happen then? Now electrons would have spilled over from the P-type semiconductor into the N side, right? Even though I have very few minority carrier electrons. And I would not form a depletion region here, I'd form an accumulation layer. Similarly, holes would spill over, because now if that's what I had done, EF1, suppose EF1 was higher than EF2, electrons would spill over from the P-type and holes would spill over this way. So I'd have formed both an accumulation in the P region and the N region, right? So the point is, it's very important that you look at the band diagram just before contact and see where the Fermi levels are to see which way the electrons and holes would flow. And depending on that, you determine whether I'm getting depletion or accumulation on the both sides, okay? So in this case, I've chosen parameters where I get depletion region here as well as over here. The bands bend to reflect that, and I form a depletion region of a certain width. In the case of an accumulation layer, as you might have seen in the previous slide, there is no depletion region. Therefore, the band bending happens over a very narrow region, all right? The hardest part, of course, as I said, is figuring out what happens right at the junction itself, right? So to make sure that you don't get that wrong, look at the diagram just before contact and you simply extrapolate those lines, okay? So you see that EC1 minus EC2, which I call delta EC, which is shown over here, is nothing but the difference between chi2 and chi1, right? So delta EC is equal to the difference of the electron affinities, all right? Similarly, delta EV, this is equal to chi2 plus EG2, chi1 plus EG1, right? So delta EV would be delta EG minus delta chi, all right? Now these rules are sometimes known as the Anderson affinity rules, okay, after the physicists who looked at that. But once again, there can be additional complications due to Fermi level pinning and all that. So this is just a 0th order model, okay? Now, going back to these values of the band offsets, I can guarantee you if you simply try to apply these equations, there's a good chance you'll get the numbers wrong because you'll be confused as to whether the signs of the delta EG and the delta chi are going to be positive or negative. You have all possible combinations, and there's a good chance you'll get things messed up. So the best way is to use this figure as a guide, right? So, and you extrapolate the lines, and then you'll get the proper values of delta EV, and you can figure out which is higher and which is lower. So for example, you can clearly see that EC1 is higher than EC2. Similarly over here, EV1 is lower than EV2, and you get this weird band offset and all that, okay? So I want you to, practice other cases on your own, and I think I've given you a homework problem because there's a good chance I'll, ask you to analyze something like that, okay? Now, once you get the band diagram, you'll get, in this case, barrier, and the rest of the story is very similar to that of a PN junction, okay? Now, one other thing that I'm showing on this band diagram that I haven't talked about so far is the concept of a so-called local vacuum level. So far, we've been talking about what's the actual vacuum level, EVAC, as shown over here, which is shown with this dotted line at the beginning, okay? And that's always the true vacuum level, okay? But you now have to introduce another concept called the local vacuum level, which is what the electron would have, the potential energy the electron would have if you pulled it out of the device, but not very, very far away, but you moved it right across the surface of the heterojunction, okay? In this case, because of the charges in the dipoles on the two sides, so you'd have positive charges on this side and negative charges, you have field lines, you'd end up doing some work across those field lines, and that causes this potential barrier, it turns out, okay? Now, the reason it's important to introduce this new concept of local vacuum level is otherwise you have sort of inconsistencies, right? Because what you find is after contact, the difference between the conduction bandage on this side to the true vacuum level seems to have increased, right? But the electron affinity is a material parameter that cannot change. So that's why if you have this new local vacuum level, you see that you have the same electron affinity after contact as you had before contact. Okay? All right, so that's all that I have about junctions, PN junctions. And like I said, there's a good chance I'll ask you to draw band diagrams of heterojunctions. And just to summarize quickly once again, you should always draw the diagram just before contact to see how the bands line up. And you can put down the values of electron affinity, band gaps, and work functions to pinpoint the conduction bandage, valence bandage, and the Fermi level. The relative alignments of the Fermi levels will tell you which way the electrons and holes spill over. And from that, you can figure out whether I get depletion or accumulation of carriers. Then to draw the diagram after contact, you first draw a horizontal line, call that the equilibrium Fermi level everywhere. Start drawing the bandages far away from the junction because you know the carrier concentrations will not have changed, and you know what the band alignments are before contact. And then the hardest part is seeing how the bands bend and link up at the heterojunction. You simply extrapolate the lines before contact, and from that you can get the band offsets and et cetera, okay? Any questions? All right, so now we are getting into really the most fun part of the course, okay? We are moving from 2-terminal devices to 3-terminal devices, okay? Transistors. Transistors, especially the metal oxide semiconductor field effect transistor, which hopefully you've seen in 438 or even 302, as you probably know, is the workhorse of the semiconductor industry, right? All your ICs, by and large, depend on the MOSFET, and that's what we'll be building up towards. Not today, but from next week. But before that, I wanted to give you a preview of 3-terminal devices or transistors, which are also known as active devices, which are capable of power gain, unlike a passive device like a resistor or inductor, which cannot do any power gain. Now, to understand this concept of gain, voltage gain, current gain, or power gain, let's look at these figures. First for a 2-terminal device, and then for a 3-terminal device. Here it's just some black box 3-terminal device and black box 2-terminal device. Okay, could be a diode, could be a transistor, could be anything. And what I'm showing on the right-hand side are some, theoretical IV characteristics of the 2-terminal or the 3-terminal device. Okay, and the important point is it's non-linear. Okay, let's not worry about exactly what the device is. The important point is it's a nonlinear IV, all right? And I've hooked up the device to a ohmic resistor with a linear IV to a voltage source E. And if I pose the problem, how do you figure out what the voltage across the device is and what current flows to the device? You really can't solve that analytically if you have some complicated nonlinear IV, right? Because clearly from KCL, you have to have the same current flowing through here as through the device, and the voltage drop through the across the resistor plus VD must add up to E, right? But I mean, how do you solve that analytically? Well, you can solve that graphically as shown on the right-hand side, okay? So what you do is, you first draw the IV of the black box device, shown in this solid blue line, and then you draw what's known as a load line, okay? Hopefully you've seen the concept of the load line in 411 or 302 or 438, but just to refresh your memory, for the load line, what you look at is the terminal values of current and voltage in terms of what appears across the black box device. Now, clearly, if the voltage drop small v sub d across the device was 0, the current flowing through the resistor should be equal to E divided by R, right? So that gives you this value when the voltage across the device is 0. Conversely, if there was no current flowing through the device, there's no current flowing through the resistor, therefore all the applied voltage E must appear across this black box device, okay? So those are the two terminal points for the load line, okay? And of course, we know that the resistor itself has an ohmic linear behavior, so you can draw this load line, and this operating point is this intersection point, right? So you know that the device will have a voltage VD appearing across that, and there'll be current ID flowing across the structure, okay? Now, once I see that, let's extrapolate to a 3-terminal device, where I add a third terminal, which I call my gate. In the case of a BJT, that'll be called the base, to modulate the current flowing through this black body device. So now, instead of having a single nonlinear IV, I get a family of nonlinear curves, which are controlled by this third terminal VG, all right? I, once again, hook it up to a voltage source with a ohmic resistor. In this case, I'm putting in specific values. So I draw the load line. So if the voltage across this black box is 0, current flowing through the resistor will be 15 volts divided by 1 kilo ohms or 15 milliamps. But if the current ID is 0, all the voltage 15 volts must appear across the device. And then I draw a straight line, and the intersection points give you what the operating point is, okay? But now, the additional catch is, I can modulate the third terminal voltage VG, and suppose initially I had a voltage of 0.5 volts on the gate. The voltage across the device, VD, is 5 volts. If I wiggle that gate voltage from 0.5 volts plus or minus 0.25 volts, say, so I go to 0.75 or 0.25, I look at the corresponding intersections, okay? And approximately, I'm not being very accurate over here, I see that when I change the gate voltage plus or minus 0.25 volts, the output drain voltage changes plus or minus 2.5 volts. You see it goes from 2.5 to 7.5 volts when the gates change from 0.25 to 0.75, right? So therefore, in this case, I get a voltage gain, which I call AV, which is the delta VD over delta VG, or approximately 2.5 divided by 0.25, or approximately 10, all right? Similarly, you can, under certain conditions, you can get a current gain. Now, in the case of a device which has a very high input impedance, the gate will hardly draw any current, as in the case of MOSFET. So it really doesn't make sense to talk about a current gain. Hopefully, the gate current is almost 0. You talk about a voltage gain. In the case of a BJT, on the other hand, that I'll discuss in a few weeks, you can have significant amounts of base current, and you can have base, you have to think of current gain, voltage gain, etc., etc. So when you get voltage and current gain, or at least one, such that the change of output power is more than the change of the input power, you get a power gain, A power, and that's what I have in an active device. Now, let's take a digression. And think of a transformer, okay? Now remember, in a transformer, you have a primary coil and a secondary coil, where typically you have more turns in the secondary than in the primary, right? And the voltage at the secondary over the voltage at the primary will be proportional to the number of turns in the secondary over number of turns in the primary, right? And in a step-up transformer, the output voltage would be higher than the input voltage, right, at the primary. So is a transformer then an active device? Any guesses?
No,
Very good. And why is that?
because it's just physics driving it. That's not really, you're not feeding it. This power in is the same as power out, theoretically.
Exactly. Yeah. So it's always physics driving it. You know, transistors are also physics.
Right.
You're absolutely right. The power in equals power out. In fact, the power out will always be slightly less because you'll waste some power through ohmic resistive losses in the transformer, right? So although I get a voltage gain, I get no power gain, in fact, a slight power loss. So transformer is a passive device. But on the other hand, in the case of an active device like a transistor, you get a power gain. Now, am I saying then that I'm creating energy out of nothing? Where did this energy come from?
From the power supply for the transistor.
Exactly, very good. So I've converted the DC power to an active AC power, right? So you still have conservation of energy, but you're converting DC power into AC power, the signal power. All right. Now, in the next few slides, I'll look at a specific three-terminal device called the JFET. All right. Now, I'll go over this relatively quickly for two reasons. Number one, JFETs are not that important these days, okay? I only show this sort of as a preview of the main course in this, the main menu, well, trying to be cute, the main course in this course, the main thing in this menu, which is the MOSFET. Secondary, because we also have lost some time, we don't have time to analyze the JFET in detail. It's not a big deal because it's exactly the same kind of analysis that we will do in detail in the context of the MOSFET, okay? So I'll go over this relatively quickly. You will not be responsible for the JFET in the final exam, okay? So do pay some attention because I think I've given you one homework problem that you can solve just by plugging in formula. But I'm not going to, ask you any questions at all in the exam, final exam on the JFET. All right, so what is a JFET? It's a three-terminal device where you control the current flow between an input, which is called the source, and the carriers flow into the drain, okay? And the current is controlled by a third terminal, the gate, as in the black box example that I showed in the previous slide, okay? Now the terminology is, the source is always a source of carriers, and the drain is a drain of carriers, okay? Regardless of whether it's electron or a hole. Now, if the carriers that are flowing were holes, we know that the current vector points in the same direction as the carrier flow, right? So if it is a p-channel JFET, the current will point in this direction. On the other hand, if it is an n-channel JFET, as in this example, although the electrons flow from the source this way, the current vector obviously is opposite to that, all right? So always source and drain, the source is the source of carriers that are flowing through what's called the channel, and they're drained by the drain, and the flow of carriers is modulated by this gate. It's kind of like a gate in a pipe, like a valve in a pipe that you can open and shut to control the flow of water. In this case, I'm controlling the flow of the carriers. In this particular case, electrons. Since electrons are flowing this way, as you can see, the current actually points opposite to that. All right. Now, you always have to have voltages reference to what's called the ground voltage. And the convention is the source voltage is always assumed to be the ground potential, okay? So your drain voltage and gate voltage are always measured with respect to the source, all right? Now let's see what would happen if I had a structure as shown over here, where I have a p-n junction, in fact, a p plus n junction. P plus meaning is highly doped in this gate region and more likely doped in the channel. And then down below I have another gate. You don't necessarily have to have gates on two sides, But in this particular example, I have a JFET with 2 gates on both sides of the channel. Okay. In practice, you typically only have 1 gate, and then they'll have a ground plane down below. And because it's highly doped P plus, we know from p-n junction theory, the depletion region extends mostly on the n side, as shown by these lightly shaded regions. Okay. Now, clearly, what you can hopefully see is, as I make the gate voltage more and more negative, I'll be reverse biasing this p-n junction. What will happen to the depletion region? It'll expand more and more, right? That will constrict the current flow through the junction. Therefore, the device will become more and more resistive. And at some point, if I apply enough reverse voltage where the depletion regions meet, I'll pinch off the channel, and that voltage is known as a pinch off voltage given by this. All right. Now, this, if you think about it, is nothing but the same kind of math. You're solving the Poisson equation as we did in the case of a reverse bias p-n junction, right? And remember, I told you that there's a very important formula from p-n junction electrostatic behavior that I want you to memorize. Well, that's the same formula over here, right? The voltage across the depletion region of a p-n junction is half Q depletion region squared, okay? Now in this case, A is half the width of the channel, okay? If that is my channel width, A is defined as half the channel width, okay? So in this particular case, I'm pinching off the channel symmetrically from both sides, okay? So for p-n junctions, we saw that the voltage across the junction was half Q W squared doping on the lightly doped side over the dielectric constant of the semiconductor. And that's exactly this formula, except that A, which is half of this channel width, is replaced for W over here. Okay? Everybody with me? Now, the other complication is, and that's what makes the 3-terminal device such as the JFET interesting, is now you have to also pay attention to the 3rd terminal, the drain. Well, what happens as I increase the drain voltage? Well, there's current flowing from the grounded source to the drain. And let's follow the channel potential. Well, at the grounded source over here, what do you think would be the potential, electrostatic potential of the voltage? The source is grounded, therefore the voltage would be
0.
0, right? Similarly, at this point, it's connected to some drain terminal voltage, VD. Therefore, the voltage over here in the channel has to be VD, right? How about along the channel? Well, initially, assuming that this depletion region is very, very tiny, it's almost like a resistor, right? An N-channel resistor. Therefore, you'll have a linear IV as shown over here, right? So the channel potential along X, which I call V of X, will vary linearly with position, initially for low drain voltages and where the gate isn't pinching off the channel completely. Now, the complication is, as I increase the drain voltage, let's see what the reverse bias is between the gate and the channel at the source end and the drain end. You'll find that the two are different, right? Because at the source end, the reverse bias is whatever the gate voltage is minus 0. So that doesn't change, right? Because the source is grounded. On the other hand, at the drain end, I'm making my VD more and more positive in this case because I'm drawing electrons this way. So that's reverse biasing this p-n junction over here, right? Now, what is the magnitude of the reverse bias? It is whatever that VG was to begin with, that reverse bias, and then I add the VD to the reverse bias, right? We have to make the signs right? So the magnitude of the VD has to be added to the minus BG to get the total reverse bias, right? And if that reaches this pinch-off voltage, the channel gets completely pinched off, and the current doesn't increase any further with drain bias, as shown in the next slide. Okay, so that's what's shown in a cartoon view over here. Okay, so initially I start out with a very low drain voltage, so the channel potential at the source end and the drain end are both close to 0. The depletion region is more or less the same thickness everywhere. It's like a linear resistor. In fact, the IV almost looks linear, like in a resistor. But the fun starts as the drain voltage keeps increasing. the effective reverse bias near the drain end of the channel is more than near the source end. Near the source end, it always stays put at whatever the reverse bias I've applied to the gate. But near the drain end, it becomes VGD, which is the reverse bias of the gate plus the effective reverse bias due to the drain voltage, right? Because there's a channel potential increase from 0 to VD, okay? Now, in the previous example, I assumed that the channel potential increases linearly because the channel thickness was more or less the same everywhere, okay? Is that the same in this case? Well, clearly not, right? Because the depletion region is more near the drain end of the channel. The channel is getting more constricted, all right? Now, what can I say about the current flow across this cross-section or this cross-section or this cross-section in steady state? In KCL, they have to be
Equal.
equal, right? So I have to flow the same current across every cross-section. But yet, I know that this part of the channel is more conductive because, you know, the cross-sectional area is more than this part of the channel, right? Therefore, to drive the same current throughout, I have to drop more voltage across a certain distance dx over here than the same distance dx over there, right? In other words, the plot of channel potential versus VD won't be linear anymore. It'll be sloping up like this, right? So lower voltage drop here, or a lower channel electric field over here, a larger channel electric field over here because of the steeper slope, okay? And they'll self-adjust to make sure that the current across any cross-section is the same. You with me? All right, so because of that, because the channel is getting more and more resistive, not resist, I mean, the resistance is going up, the channel resistivity rho doesn't change. Rho is given by 1 over sigma, which is 1 over Q mu n, that doesn't change. But the resistance, which is rho times cross-sectional area divided by L, which is rho times the width of the channel times the width of the device, which in this case I call Z, because the dimension perpendicular to the plane of the board is Z, divided by the channel length. So basically what happens is, as you go from the source to the drain, the effective width of the channel is reducing, and therefore the sorry, I think I messed up. Yeah, rho, sorry, I messed up. So it's rho L over A. Got the flip, sorry, my apologies. So let me write it down again. Let me erase it. Just a second. I don't know how to use it. Eraser, sorry. Let me write it again. So that's rho L over A. A is width of the channel times width of the device itself measured in that direction, okay? So the width of the channel is gradually going down, therefore the resistance keeps going up. And because of that, the curve starts bending over, okay? And at some point, the channel gets completely pinched off and the current saturates. That's called your ID sat. And that corresponding voltage is called VD sat, okay? So putting that along with the gate voltage, now what you'll find is in a JFET, or in fact all field effect transistors, you get a family of curves, which initially for low drain voltages will be like a linear resistor. But then as the drain voltage increases, the reverse bias between the gate and the channel near the drain end becomes more than near the gate and the source. If the curve starts bending over, then it'll saturate at whatever ID sat is at the corresponding VD sat, sorry. ID sat is at the corresponding VD sat, okay? But of course, don't forget the third terminal. So this first curve was if the gate itself wasn't reverse biased directly. But if I apply additional reverse biases, you then have a depletion region from the get-go, and therefore the channel gets pinched off earlier at a lower drain saturation current. You get a family of curves like this, okay? You can then hook up this device to a external load resistance, R, okay? And then you draw the load line and you get the voltage gain and the power gain, as I mentioned earlier on. All right? So the mathematics of this that I'm not going to discuss in detail, and like I said, you won't be responsible for this in the exam shown over here. It's very straightforward, actually, okay? So you write down the current using the formula of the resistor. I, we know, is given by voltage divided by resistance, okay? Where resistance is rho L over A. I bring the A over to the numerator. Now the A, in this case, is this quantity over here, okay? That's the width of the channel, width of the transistor measured perpendicular to the plane of the board, okay? Not the width of this channel W over here. So let me try to sketch a figure in 3D, if you will. Okay, so this is sort of an isometric view, if you will. Okay, so that's my gate. So what I'm calling the width of the device, Z, is in this direction. The carriers are flowing this way. And then if I look at the three-dimensional view, that's a channel. That's what I'm calling the channel width. Okay? You guys with me? So the cross-sectional area for current flow is this dimension times this dimension, right? So that's Z times 2 times HS, H, where H is the undepleted part of the channel. And I'm calling 2 times that because I have assumed a geometry that's symmetric. So I have H plus H, or 2H, but that is a function of position X along the channel, okay? Now, when I apply a voltage, the channel is getting more and more constricted. Therefore, the V of X versus X is not going to be a straight line, but it curves over, meaning that the electric field near the source end of the channel is lower than near the drain end. And the electric fields have to self-adjust so that the current at any cross-section has to be the same in steady state, as I mentioned. All right? Now, what is this electric field? That's given by minus dV dx, okay, with the minus sign. Okay? Now, the way I write down the current in a resistor R is current is equal to V over R, which is rho L over A. Okay? I bring over the A in the numerator. Now, V over L is, of course, nothing but the electric field of a resistor. Rho is 1 over sigma. So if I write it in terms of electric field and sigma, this V over R works out to V over L, which is electric field. A equals the device width times the thickness of the channel, 2HX, right? And then rho in the denominator, right? So that's what I have over here. All that I'm doing is I'm replacing the electric field, V over L for an ohmic resistor, by this position-dependent electric field over here, dV dx. All right? Now, once I have that, you can convert this, you can integrate this differential equation by bringing dx over to the left-hand side and integrating from the source end of the channel to the drain end. I call the channel length L, okay? And on the right-hand side, you integrate this undepleted part of the channel H of X with respect to V of X. That integral has to be between 0, the source voltage is grounded, to VD. So those are the limits of integration, right? Now, what is H of X, the undepleted part of the channel? That's the original channel half width A, shown over here, minus the depletion width W, which is a function of X, right? And we've already seen what the formula of that W is in terms of the voltage drop between the gate and the channel at some location, which I call VGX, which is Vx minus Vg raised to the power half. Why do I get that? Well, use that famous formula that I keep talking about for the PN junction, relating the voltage across the depletion region to the depletion width, or by taking the square root of that, you get a square root dependency between the depletion rate and the voltage, right? So basically, that's what I'm applying. I'm not going through every single step, as I mentioned. You should look through the math yourself, convince yourself at home, and so that you can solve the homework problem, but you don't have to study for this for the finals, all right? Because, like I said, JFETs are not that important these days. And plus, we go through exactly the same analysis in more detail in a week or two in the context of the MOSFET, where we'll see that the gate is made by what's called the MOS gate, a metal oxide semiconductor. And the channel is not formed by doping as shown over here. A channel is formed by inverting the semiconductor by applying suitable voltages. But the term inversion means I start with an N-type semiconductor maybe, and applying a suitable gate voltage, I electrostatically convert it to P-type and vice versa. But that's next week. All right, so anyway, if you do this simple integral, on the left-hand side, if I integrate ID dx, ID, of course, is independent of x. On the left-hand side, I'll simply get ID times the length, because I'm integrating dx between 0 and L. On the right-hand side, I integrate from Vx of 0, where the source was grounded, to Vx of Vd, and putting in those limits, that's this current voltage characteristics that depend, which depend both on the drain voltage and the gate voltage. And you can then re-express that in terms of this pinch-off voltage, as I had in the previous slide, where the pinch-off voltage is the voltage that you need to completely pinch off the channel, okay? You can also come up with an expression of this ID sat, which is this value that the current saturates at, okay? Now, it turns out this property of the device to saturate the current is a very important characteristic, okay? Because what that tells you is, let me ask you, if I have this sort of a characteristic, can anyone tell me what the output impedance of the device is in saturation? This part of the device is known as a linear region, and that part of the device is known as the saturation region, where the current saturates. Well, if the current saturates, what is my output impedance of the transistor in this region? High or low? Anybody? Impedance of a device is given by change of voltage divided by change of current, right? Here in saturation, I can change the output voltage a lot, but not change the current much at all, right? Therefore, I have a very high output impedance. And that turns out to be very important for many circuit applications, okay? In the case of a JFET, the input impedance is also pretty high because the PN junction that I'm looking at is a reverse bias junction, okay? But it's not super low because in a PN junction, we've seen you can get some leakage currents, right? In a MOSFET, on the other hand, that we'll discuss next week, we'll see we have what is called a metal oxide semiconductor structure. And since an oxide is a dielectric, the input impedance of a MOSFET is also going to be very, very high. Okay, so much for the JFET. There's another device very similar to the JFET. I call it the cousin of a JFET, which is called a MESFET. Stands for Metal Semiconductor Field Effect Transistor, where it's exactly the same kind of structure, except that I gate the channel, in this case, N channel made in gallium arsenide, made on resistive gallium arsenide substrate. So I don't have any current flow in this highly resistive substrate, but I have current flow in this N-type channel that's formed by doping. Once again, I have a source of carriers and a drain of carriers. If this is N-type, it's electrons which are sourced this way, meaning the current actually flows opposite to that. And that's why the drain voltage is positive. So the drain current is flowing this way through this channel. And the current is controlled by this third terminal gate. But now the gate is not formed by a PN junction, but is formed by a Schottky diode, a metal, which is shown in this dark region, to the semiconductor. On the other hand, the metal semiconductor contacts in these source and the drain regions have to be ohmic contacts, okay? Now, mind you, I told you that for a particular type of metal, you generally will not get an ohmic contact and Schottky diode under all conditions, right? So due to that, what's done in a MESFET is you purposely dope the source and the drain regions very, very heavy near the source and the drain regions. You make those regions N plus, so that any Schottky barrier would have a narrow tunneling barrier, so that it would act like an ohmic contact near the source and the drain. But you don't do a high doping in the middle part of the channel, and so that it can form a depletion region as in the Schottky diode. Okay, but as I said, because I'm flowing current as in the JFET, the thickness of the depletion width is more near the drain end than near the grounded source. As the drain voltage keeps increasing, at some point, the channel gets pinched off, and once again, I'll get saturation of the drain current in a MESFET. Now, MESFETs are also not used very commonly, but at least they're more common than a JFET, because not so much for silicon devices, but for compound semiconductors, MESFETs are sometimes used because they have the benefit of being a very simple device, right? Because all that I need is a doped semiconductor layer, and you slap down 3 contacts, 2 ohmic contacts for the source drains, and a Schottky diode contact for the gate, and voila, you have a transistor, right? Besides, it turns out these transistors also have the property of being super high speed. So for very high speed transistors, sometimes MESFETs are still used. Another variation of this concept, which is also not widely used, but used for super high speed devices, is called a MODFET. That's shown down below, a modulation doped field effect transistor. Okay. Now I'm showing the band diagram of such a structure. And just to make sure that you understand the band diagram, what the channel now is, it's not just a gallium arsenide channel, but it's made up of a high band gap aluminum gallium arsenide layer, AlGas, with a low band gap gallium arsenide layer, and then down below another high band gap aluminum gallium arsenide. What I do in this band diagram is I take a cut as a function of depth, and I turn the figure by 90 degrees. So now the aluminum gallium arsenide barriers are on 2 sides, and the gallium arsenide channel in the middle is shown over here. Okay, I'm only showing the conduction bandage. The valence bandage will be somewhere over there, like so. All right. Now, what we do in this concept of the modulation doped field effect transistor, which is also sometimes known as a high electron mobility transistor, or HEMT, is use a concept called modulation doping. What does that mean? Well, in modulation doping, you don't dope the channel itself directly. Here, the channel is going to be this gallium arsenide layer. You don't put the dopants in the channel. Instead, you put your dopants, the donors, in the high band gap aluminum gallium arsenide on the 2 sides, where the donors contribute the electrons in the conduction band, but because they see this potential well in the gallium arsenide, the spillover as shown over here. Okay, so that's why it's called modulation doping. I'm modulating the regions which are doped, and I separate the regions where the doping donors are from where the carriers ultimately end up in. Why do I want to do that? Well, recall that in chapter 3, when we talked about transport, we said that when carriers move in a semiconductor, if it's a perfect semiconductor crystal, there will be no collisions or scattering, right? Who remembers what causes collisions or scattering of carriers? Is it bumping into the periodic arrangement of atoms in the crystal?
It's defects in the wave
Very good.
propagation.
Excellent. Okay. Now, what are the types of defects? Well, there's many kinds, but 2 that are unavoidable are these lattice vibrations or phonons at finite temperature. And the other one that's unavoidable is ionized impurity scattering because of the doping, right? Because you have to dope the device to get functionality, right? So you're kind of stuck with these intentional defects. Now, on top of that, you could have other unintentional defects also, but hopefully with good engineering, you can get rid of that. But the doping will cause defects, ionized impurities, and that reduces the mobility. So that's the problem that I try to solve using this concept of modulation doping. I put the carriers in a region where there are no dopants. So now these carriers can move in this channel in the direction perpendicular to the plane of the board. So they can move in this channel, which is undoped, but I still get the carriers from the gas, AlGas layers. And that's why I can get very, very high mobilities. How high? Well, just for calibration, in gallium arsenide, for electrons at room temperature, you have a mobility of 8,500 centimeters square per volt second. Okay, so that's gallium arsenide, room temperature, 8,500. All right. If you dope the thing, you'll drop quite a bit. You know, for modest doping, you may drop to a few thousand. In a modulation dope structure or a HEM structure, these mobilities at low temperatures can go up to a couple of million. Okay, because at low temperature, I've gotten rid of the, reduced the phonon scattering, plus I've gotten rid of the ionized impurity scattering through this crate, right? So what I'm showing here is at this hetero interface between the Al gas and the gas, that's a diagram on the side. So this shows just a conduction bandage. I get the carrier spilling over, the Al gas gets depleted, the gas layer forms a layer of electrons, okay? This is called a two-dimensional electron gas because it's almost like a two-dimensional sheet of carriers at this interface, which can travel with very, very high mobility between the source and the drain, okay? So these devices are not mainstream devices, but they're used where you need super high frequencies or super low noise, as in, you know, front-end amplifiers of radar and things like that. And it turns out this is a very nice platform for doing all kinds of cool physics, okay? Believe it or not, this particular device structure over the years, over the last 30 years, has led to about half a dozen Nobel Prizes in physics, okay? Starting in the 1980s with something called the quantum Hall effect that you might have seen, followed in a few years later by the fractional quantum Hall effect, and then a whole bunch of other very, very interesting physical phenomena that people have been able to study in this highly idealized two-dimensional system. So a lot of deep physics in it, and then some practical applications also. So in these MESFETs and the HEMs, okay, if you make them very, very short channel lengths, what's going to happen? Well, for very short channel lengths, if the electric field goes up and you look at the drift velocity as a function of electric field, what did I see? Well, for low fields, we know that the drift velocity increases with the electric field, where the slope is given by the mobility, so it's mu times E, but at high fields, it'll saturate at some saturation velocity. Remember that? Well, it turns out in these short channel devices made out of these HEM structures or MOSFET or MESFETs, or even in MOSFETs and JFETs, if the channel length is very, very short, the electric field along the channel, which is roughly speaking of the order of the drain voltage divided by the channel length, that's your rough electric field, can be very, very high, where I'll no longer be in the ohmic region, I'll be in the saturation region, okay? And once I have that, then the carriers throughout the channel will travel basically as fast as they can, which is the saturation drift velocity, okay? Under those conditions, one finds that the drain current will increase more or less linearly with the input gate voltage. So these are equispaced curves, unlike this nonlinear spacing between these curves that you have in a long channel JFET or a long channel MOSFET or whatever, all right? It turns out such nonlinear spacing is not very good from a circuit design point of view, because that then introduces nonlinearities of the gain between the input and the output. On the other hand, if you have linear spacing of the curves and you draw this load line, you get a nice linear gain characteristics between the input and the output, okay, because the spacings are uniform. Now I'll go through the derivation of this once again in detail in the case of the MOSFET, but you can kind of get a preview of why the current varies linearly like this. So you'll see that the current is going to be proportional, will be equal to the width of the device, which I'm calling Z, times the thickness of the channel, say W, in the vertical direction in this case, okay? That's the cross-sectional area. And the carriers will then travel at saturation velocity, right? Now, what is the current due to then? Instead of mu times E, there'll be Vs. The carrier concentration is N per unit volume. And then the charge of the electron is Q. Now, this N in the short channel devices and with suitable structures will be basically proportional to the gate voltage, okay? So we'll go through this derivation in detail in the context of the MOSFET, but basically we'll find that because the carriers are velocity saturated, you end up getting uniform spacing between the output drain current and the input gate voltage, which is a very nice feature from a circuit linearity point of view, okay? All right, so that's all that I have. So next week is going to be a very important set of lectures because I'm going to give you a lot of problems in the final exam. in the context of the MOSFET. Okay, so now it's a 3-terminal device. Once again, you have a source, drain, but now you have a so-called metal, dielectric or an oxide in between, and then the channel, and that gives rise to the MOSFET structure as shown over here. That's what we'll start off with next Monday. Thank you. Any questions? Well, all these lectures are being recorded on the cloud, and I'll publish them at the end of the day. All right, see you Monday. Thank you.